independent events. So we did conditional probability, which is dependent events. And in dependent events, you have to be doing the same thing, right? And your keywords are without replacement. So dependent events, what that means basically is if you're drawing marbles out of a bag of marbles, then you're two events. And keep in mind, dependent, independent involve two things. You've done two things. Mutually exclusive or non-mutually exclusive involve the probability of one event. And where we look for the mutually exclusive or not is, can both things happen in one event? I draw one card. The probability that it is a heart or a 10. So mutually exclusive, non-mutually exclusive, the key word is or probability. Dependent events, independent, the key word is and. It is an and probability, right? Let's write that in here. And, okay, and probability. So in dependent, we don't put things back. So you got to be doing the same thing. You got to draw a marble and then not put it back and draw another marble. Independent events are events whose outcomes are not affected by each other. So it could be two totally different things, right? Like drawing a card and flipping a coin. So when you draw the card, that would have absolutely no effect on you flipping a coin. If you are doing the same thing, okay, like flipping a coin twice, then if you flip a coin twice, the first flip has no effect on the second flip. If you're choosing items, then you will see the words with replacement or put back. Okay, so a card is drawn, put back, then another card is drawn. In dependent events, a card is drawn, and then without putting it back, without replacement, another card is drawn. Independent events, another card is drawn after it's put back. Or you draw a marble out of a bag. You put it back, and then a second marble is drawn. So in both of these cases, or in independent events, when you do the second thing, you are back to the initial starting condition. So you're either doing two totally separate things, draw a card, flip a coin, roll a die. So they can obviously have no effect on each other. If you're doing the same thing, then on your second draw, you're back to the initial starting conditions. An independent probability does not depend on the probability. Your formula is this. This is the one on the formula sheet. It's an and. Okay, so intersection is and, right? Both things happen. So, given this formula, and this not new cost, determine if events A and B are independent. So they are independent if the probability of A and B is equal to the probability of A times the probability of B. So that would mean 0.2 is equal to 0.6 times 0.4, which would mean 0.2 is equal to 0.24, which it isn't, so no. So all we can say is they are not independent. Okay? We can't say anything else. We can't say they are dependent. We can just say they are not independent. In this one, again, always start with the formula. So here's my formula. Off the formula sheet. Is 0.56 equal to 0.8 times 0.7? Is 0.56 equal to 0.56? And we can say yes. So these events are independent. Are independent. This is my 5th lesson of the day. There are 3 children in the Smith family. Determine using a tree diagram the probability that 2 of the 3 children are girls. So here's the first child. So this is a case where we really want to list the sample space. As you can say, if I have a family of 3 children, I could have 3 girls, I could have 3 boys, I could have 1 girl, and 2 boys. I could have 1 boy and 2 girls. So we could say there's 1, 2, 3, 4 outcomes, right? But there aren't really 4 outcomes. We need to list these. So we'd say the first child could be a girl or a boy. If the first child is a girl, the second child could be a girl or a boy. The first child is a boy, the second child could be a girl or a boy. The first child is a girl and the second child is a girl, then the third child. Okay, and you've got the idea. Okay, now you think about this. There are not 4 outcomes, right? Fundamental counting principle says first, second, third. There are 2 choices for the first child, girls or boys. 2 choices for the second. There are 8 outcomes. And our question is, of those 8 outcomes, how many are this, how many are this, how many are this, and why did you put a big X through them? So we follow each branch with girl, 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 boy, girl, boy, girl, girl, boy, 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 girl, girl, boy, girl, boy, 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 girl, boy, boy, boy. So determine the probability that 2 of the 3 children are girls. Okay, so 2 G's and a B. Then we have 1, 2, 3 outcomes, 3 out of 8. Okay, so sample space lists all the outcomes. This is a way of counting it. 1, 2, 3, 4, 5, 6, 7, 8 outcomes, right? As the fundamental counting principle said we should. Probability of all 3 girls is 1 out of 8. Probability that all 3 are boys is 1 out of 8. Probability that there are 2 girls and a boy is 3 out of 8, and probability that there are 2 boys and 1 girl, 2 boys and 1 girl, is also 3 out of 8. And so those probabilities, so 1 out of 8, 1 out of 8, 3 out of 8, 3 out of 8, that's all that can happen, right? 3 girls, 3 boys, 1 of each, 1 of one and 2 of the other, etc. is 3, 6, 7, 8 out of 8. That has to add up to 1. Okay? Each of these individual probabilities, right, is one of the 8 outcomes. So the probability of having 2 girls, then a boy as the youngest is 1 out of 8. Probability of having the boy as the middle child is 1 out of 8. Probability of having the boy as the eldest child is 1 out of 8. Okay, so each of these specific outcomes has a probability of 1 out of 8. All right, let's roll the dice. A die is rolled twice. Determine the probability of each situation, either using a tree diagram or the chart. Okay, so usual tree diagram, we've got a blue die, we've got a red die, all right, that's the first one was the blue die. And generally with dice, right, we work out, we show the chart so we can see there are 36 outcomes. So what's probably the first roll is a 2. So the probability of getting a 2 on the first roll is 1 out of 36. And the second roll is a 5. Now, these are independent events, right? The fact that you rolled a 2 on the first roll, when you go to roll the dice the second time, there's no effect that rolling the 2 the first time had. Okay, so use a tree diagram, right? So we say, all right, first roll is a 2. First is a 2. Well, a 2, and I'm going to use this. This is not a 2. And then a 5, and this is not a 5. And this is a 5, and this is not a 5. So in a tree diagram like this, the first roll is a 2, is 1 out of 36. Probability of getting a 5 is 1, 2, 3, 4 out of 36. What should we put? Let's put probabilities 4 out of 36. So the probability of getting a 2 and then a 5 is 1 out of 36 times 4 out of 36, which is, calculator, on brackets, 1 divided by 36. So anybody can do this on any calculator, times 4 divided by 36. Okay, I want to go straight to a fraction. So I'm going to go math, enter, enter. We get 1 out of 324. 1 out of 324. Now, if we do each of these probabilities, so the probability of not getting a 5, remember, these guys have to add to 1, right? So this will be 32 out of 36. This will be 35 out of 36. This will be 5, 1, 2, 3, 4. So again, 4 out of 36. And this will be 32 out of 36 as a probability. If we worked each of these out individually and added them up, it would add up to 1, right? So are they all going to come out to 324? Probably not. See, so here's a problem with, if I reduce these, if I'm using my, well, you know what, here, let's just do them all. So we got 1 out of 36 times 32 out of 36. So I'm just going to go back up here, grab that, change the 4 out of 36 to 32, 3, and I got to insert my 2. Okay, so that's 2 out of 81. 2 out of 81. You know what? 1 out of 36 times 4 out of 36. 1 out of 324. 1 out of 36 times 32 out of 36 is 2 out of 81. What's next? 35 out of 36. So 35 out of 36 times 4 out of 36. And then 35 out of 36 times 32 out of 36. All right, so 35 out of 36 times 4 out of, so I'm going to go up here, grab this one, and then edit the 1 to be a 35. So we're going to put in a 3, insert a 2, which should be a 5. And we get 35 out of 324. 35 out of 324. And 35 out of 36 times 32. So let's just grab this guy, bring it down. Change the 4 to a 3, insert 2. And see, that's 70 out of 81. And here's the question. What do these all add up to? So let's just grab them one at a time. So that plus the 2 out of 81 plus 35 out of 324 plus 70 out of 81. Hit enter. And no surprise here, right? These must add up to 1. Okay, it's got to have every possibility. So the first roll is a 2. So probability of 2 and 5 is the probability of 2 times the probability of 5 is 1 out of 36 times 1, 2, 3, 4. That's 4 out of 36, which is that 1 out of 324. So the tree diagram, yeah, I'm not sure that really helped. I would have just used the formula. First roll is greater than 4, and the second roll is even. Okay, greater than 4, which is basically everything below that line. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. Okay, I'm not counting all of these guys. Okay, hang on. Let's do this. Greater than 4. Let's just count 1, 2, 3, 4, 5, 6. There are 6 rolls that are 4 or less. So then there are 36. So probability of greater than 4 and even. So the probability of greater than 4 times the probability of even. All right, so 1, 2, 3, 4, 5, 6. So 30 out of 36 are greater than 4, and even is half the numbers, right? We did this a while ago, 18 out of 36. So 30 out of 36, let's get fancy, alpha F2, alpha F1. So 30 out of 36 times alpha F1 numerator 18 out of 36. 18, 36. And when you enter them this way, you go straight to fraction. Right? It's 5 out of 12 equals 5 out of 12. A bag contains 5 red marbles and 7 green marbles. A marble is drawn, replace. Okay, as soon as you see the word replace, you are thinking, or should be thinking, independent events. Which means this formula, probability of A and B is simply the probability of A times the probability of B. The denominators in both these cases will be exactly the same. Use a tree diagram to analyze the scenario, state the various probability. Okay, so you could have red, hang on. You could have red, then green, then green, then red. And you can have a red first, then a green. If you draw a red first, then you can have a green. If you draw a green first, then you could draw a green. You know, I want to keep these. So let's put G down there and R up here. So we're doing red on the first draw, or green, then red, then green, etc., etc. So we'll do each probability. 5 red marbles and 7 greens. The probability of getting red is 5 out of 12. Keep in mind these have to add to 1, so that's 7 out of 12. Probability of getting red is 5 out of 12. Now in a dependent event, that would have changed to be 4 out of 11. The probability of getting red is always 5 out of 12. Probability of getting green is always 7 out of 12. Right? And the reason is you are replacing. So we have 5, so the probability of red and red. Probability of red and red is probability of red times probability of red. It's 5 out of 12 times 5 out of 12. You know, if I'm going to add these together, let's just keep it. That'll be 25 out of 144. Probability of red and green is the probability of red times probability of green. 5 out of 12 times 7 out of 12 is 35 out of 144. Probability of green and red, because we're going to analyze this scenario, right? Probability of green times probability of red, 7 out of 12 times 5 out of 12 is 35 out of 144. And the last probability is green and green. Probability of green times probability of green. 7 out of 12 times 7 out of 12 is 49 out of 144. So 35 and 35 is 70. This is 95. So take 5 away from this. Will be 100 and then add 44, right? So we can see they add up to 144 out of 144, which is 1. And that means we've taken every possibility into account. Now, analyze this scenario and state various probabilities. So, it can work this way. So, the probability of getting 2 reds is 25 out of 144. Right? So, probability of 2 reds being drawn, when you put back, is 25 out of 144. The probability of getting, I want to say this, write it down, but, okay, so the probability of 2 reds is 25 out of 144. The probability of getting 2 of the same color, let's say, right? The probability of getting 2 of the same color. Probability 2 of the same color. Well, you think of it as the probability of 2 reds or the probability of 2 greens. Now, the probability of 2 reds is probability of red times the probability of red. Probability of the 2 greens is probability of green times the probability of green, which is 25 out of 144 plus 49 out of 144, which is equal to 74 out of 144. Now I'm just going to leave these as out of 144. This should be reduced. Okay, it's like 37 out of 72. All right, I'm not going to. So 37 out of 72. Okay, which is a little over half the time, right? So 36 out of 72 would be half the time. So the probability we get two of the same colors is a little bit more than half. Probability that the probability that we get a red and a green. Probability of red and green. Now, here's the thing, that you could state the probability of getting red and then a green, or followed by a green, which would be this line here. You could say the probability of getting, you know what, let's rephrase that. What if we say the probability of one red, one green? Okay? So, if it was a red, then a green, we do this line at 35. If it was a green, then a red, we do this line. But if it's one red, one green, then we're going to say that's equal to the probability of red and green, or the probability of green and red, which is 35 out of 144 plus 35. So the probability of getting one of each color is 70 out of 144, or 35 out of 72. So the probability of getting one of each color, right, which means we got a red followed by a green, or a green, or, which is plus, right, or a green followed by a red. Probability of getting one of each color, as opposed to the probability of getting a red followed by a green. Right, that's that specific 35 out of 144. So when we're reading this, we really have to watch our interpretation. Right, so another way of saying this is probability of one of not one of each color. Student activity is having a raffle, and they have sold 200 tickets. There will be 2 draws. After the first draw, that ticket gets put back into the mix. Ms. McKay purchased 4 tickets. Determine the probability that she will win at least one prize. All right, too many trees. Okay, well, wait a minute. Probably that she will win at least one prize. So how many prizes? She wins 1 prize, or 2 prizes, or 3 prizes, or 4 prizes. So if we take a look at this, let's call this a win, and this is not a win. This is a win. Oops. This is a win. This is not a win. This is a win. This is not a win. So the probability of every win is 4 out of 200. And the probability of every not a win or loss, if it's a loss, is 196 out of 200. So 4 out of 200, 196 out of 200, 4 out of 200, 196 out of 200. Now, we can add this. This would be she wins both. This would, or sorry, 2 draws. She wins both draws. All right, change this. It's like 1 win, or 2 wins, 2 wins. This is the probability she wins both. This is the probability she wins the first. Probability wins both. Both. Probability she wins the first. Wins first, not second. Probability she does not win first. Does not win first. And does win second. Win second. And there's a probability of no wins. Neither first nor second. So we figured out, of these 4 probabilities, what we really need to do is come up with a quick way to get these 3. And here's the quick way. So the probability of at least one win, is equal to 1 minus the probability of no wins, which is 1 minus probability of doesn't win and doesn't win, which which is 1 minus the probability it doesn't win, since it's replaced, then these are independent events. So it's 1 minus 196 out of 200 times 196 out of 200, which is 1 minus, let's go here, let's do this, 196 out of 200. Now, instead of multiplying it by itself, let's just square that. And we get 99 out of 2,500. That makes perfect sense. 99 out of 2,500, right? I have no idea what the heck does that mean. So let's convert it to a decimal. 0.0396. Let's make that a percent. So 3.96%. 3.96%. And what did they say? Nearest tenth of a percent. So 4%, right? Or sorry, 4.0%. So she has a 4% chance of winning at least one prize, right? And the way you could do that is you could work out each of these 3 probabilities. We're going to do that. We have time. So, it's not like I'm going anywhere. So 4 out of 200, basically squared, right? Where's my squared? Squared plus 4 out of 200. 4. Oh, don't do that. 4 out of 200. 200 times 196 out of 200. 196 out of 200. Now, 4 to 200 times 4 to 200, yeah, squared. 4 to 200 times 196, or 196 times 4. So you know what we're going to do? We're just going to go times 2, because there's 2 of those, plus, and then the last one is oh, yeah, we don't need the last one, right? We need these 3. So just get rid of that plus. So in theory, I hit enter, we get 99 out of 2,500, because I did fractions, right? 2 decimal will be the same, times 100. So even if you work it out the long way, this plus this plus this, which are the ones where she won both, won the first, not the second, won the second, not the first, which is at least 1 win, still 4%. Holly and the bag of Smarties. Holly has a bag of blue and red Smarties, 10 red and 8 blue. Manny has another bag of Smarties, 5 red and 13 blue. Determine the probability that Holly chooses a red Smartie and Manny chooses a blue Smartie. So this is Holly, this is Manny. This is red. So we'll go red, blue, red, blue, red, blue, 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 blue. So for probability, right? Probability that both are red, probability that the first is red and the second is blue, the probability that the first is blue and the second is red, and the probability that the first is blue and the second is blue. So, all right, so Holly chooses a red. There are 10 reds out of 18. Holly chooses a blue. This has to add up to 1, so there are 8 blues out of the 18. Manny has another bag, 5 red and 13 blue. So 5 out of 13. So blue, 13, oh, 18. All right. That's an 18. 13 out of 18, red, 5 out of 18. 13 out of 18. So these are independent events because Holly and Manny are independent people, So the fact that Holly chooses red does not diminish the number of Smarties in Mandy's bag. So Holly chooses the red and Mandy chooses blue is this branch. So the probability of Holly red and Sammy blue is simply the probability of Holly red times the probability of Sammy blue. Independent, Holly red, 10 out of 18. Sammy blue, 13 out of 18 is, I don't like stringing it, but it's 130 out of 18 squared. I'm going to guess 364, but I'm going to guess I might not know. 18 squared. 324. 24 is, so as a reduced fraction, because probability is often, that you can think of that as a raw fraction. Let's insert the divide. So that's 0.4, blah, 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 enter, enter, is 65 out of 162, is 40.12%, 40.1%, or whatever. They both choose a blue. So the probability, now you don't really need the tree diagram for this, right? So Holly blue and Sammy blue is the probability of Holly blue times the probability of Sammy blue. So Holly blue is 8 out of 18. Sammy blue is 13 out of 18. 8 times 10 is 1 is 80, and 24 is 104 out of 324. 52 out of 162, 26 out of 81. I think that might be right. Let's find out. All right, let's use fancy fractions. Remember, if you don't have the fraction key, you don't need to worry about it. 8 out of 18 times fancy fractions 13 out of not 3. See, that wouldn't work. I'm going to insert a 1. 13 out of 18, enter 26 out of 81. Still got it. The second last example of the course. And now Holly chooses one red Smartie followed by another. Now this is just Holly. So the probability of Holly red and Holly red is, and we're going to assume the Smartie gets eaten. So you are not going to draw a Smartie and then put it back. All right, I know, it's all just the same stuff. HR. So the probability of Holly red, the first Smartie drawn being red, is 10 out of 18. The probability that the second Smartie drawn is red, well, there are 9 red left out of 17. Okay, so in a dependent probability, if it's both the same thing, right? If it was blue, then there'd be the 8 blue left. But what's left? There are 9 reds left, because she just ate one. And there are 17 Smarties left, because she just ate one. And that's 90 over, all right, wait, if that's 324, then that's got to be 17 less. Right, 18 less. So that's 316. 45 over half of that, 158. Is 3 going to that? 3? No. 9? Well, 3 doesn't go to that. Is that it? I don't know. Let's find out. Here, bracket this. Right? So 10 out of 18. So this will work on anybody's calculator. Times 9 out of 17. Help if that was a 9. Won't really work on anybody's calculator if that's not 9. Hit enter. Math. Enter. 5 out of 17. Really? Right. What's 18 times 17? 306. Well, you can't do that, can you? 153. Guessing 9 goes into that 5 times it. 9 goes into 153. 963. 17. All right. Use your calculator. What is there for? or 29.41%. So wholly only dependent probability this time. All right, so I haven't put the review stuff up yet in Schoology. I will do that. We'll get all of this done. This has to be exported and uploaded, and hopefully that'll all happen shortly.